Good afternoon, welcome to this video for the 2020 Level 3 Wave paper. So my pronunciation for some of these Amari words may not be very precise, so I apologize for anyone that I might offend in this video, but I'll try my best to pronounce them the best I can. So question 1, the KOO. The speed of sound in air is 340 meters per second. Okay, Amari KOO is a short flute carved from bone. This instrument can be modeled as an open pipe of length 0.155 meters. On one occasion, Manu covers all the holes and plays a note that has the following displacement standing pattern for one of its harmonics. So as we can see here, the KOO has an open end on both of its ends, which means that an antinote will be formed at both of these open ends. So we're going to be counting to determine the harmonic. The way I like to do it is that I usually count the number of, if it's an open pipe, then I will count the number of nodes in between the two antinodes, which in this case is 4. If it was two closed ends at both sides, I would count the number of antinodes in between the two nodes. So in this case, we have 4 nodes in between the two antinodes at the open ends. So this will be the 4th harmonic. Question B, calculate the frequency of the standing wave above. So we know that V equals to F lambda, and we know that the speed of air is 340 meters per second. We know that the length, so for the 4th harmonic, we know that lambda equals to 2L over N, when N is the harmonic number. So wavelength equals to 2L over 4, which equals to L over 2. So lambda equals to 0.155 over 2. If we get a calculator here, that gives us an answer of 0.0775 meters. We can use V equals to F lambda to find the frequency of the standing wave. So 340 equals to 0.0775 times of our frequency. Alright, we should get the answer of 4,387 Hertz. And if we can round this, to 3SF, which is 4,390 Hertz. The first question here should just be achieved question here. Sorry, we don't use U, we use A. So achieved question here. And this question B should be another. Could be a merit level question, okay? And achieved could be finding the wavelength. So question C, opening and closing holes in the KOO can produce different notes. Manu opens the last hole and plays a note. So the top 2 holes remain closed. Alright, so originally when we had our 4th harmonic played, in this case we had all the holes were closed, meaning that the only 2 open ends were at both ends of the KOO. But in this case, when we have question C, one of the holes is opened, which means that the open end is actually located, the new open end is now located closer to the so the new open end is now here, which is closer to the other open end, so the effective length of the KOO decreases. If the effective length of the KOO decreases, then the wavelengths that can fit the KOO will also decrease because the length needs to be a multiple of half the wavelength in order for a standing wave to be produced, meaning that for a particular harmonic, since the length has been reduced, that means the wavelength of that particular harmonic will also decrease. Since the speed of the wave will stay the same, the speed of the wave depends only on the medium. We didn't really change the properties of the medium, which means the speed of the wave inside the KOO will remain the same, meaning that since V equals to F lambda, F is inversely proportional to lambda, meaning that our frequency will actually increase. Okay, so since our wavelength decreases. Alright, so you can see that it's now closer than before. We can just say closer than the effect since the length is a multiple, so we can link that to lambda equals to 2L over n, or we can say that L equals to n lambda over 2, so we can see it's a multiple of half a wavelength, so L equals to lambda over 2. So therefore the wavelength of the fundamental will decrease. Alright, so we can say since the medium is the same, so we can say since the medium is unchanged, the speed of the wave in the co-OO stays the same. So V equals to F lambda, we can say that F is inversely proportional to lambda, therefore frequency will decrease. Frequency of fundamental will decrease. Oh, sorry, wavelength decrease, the fundamental will increase, my bad. Frequency of the fundamental will increase, okay. Explain how a standing wave is produced in the co-OO and open pipe. So for this question, we can say, okay, so we can start this question by saying, like, when the person blows into the tube, a range of frequencies is sent down into the co-OO. The waves that have the correct frequency or otherwise have the correct wavelength that fits the length of the co-OO, they can produce a standing wave, because at the open ends, the open ends will act as a will add as a free end, meaning that there's no phase change when the reflected wave reflects from the open ends. They will interfere constructively with the incoming waves, and since there's constructive interference, this will cause an antinode, which is an area of maximum displacement. In between the two open ends, there will be a numerous number of times when there is destructive interference forming a node, and there could also be antinodes between the two open ends, and that depends on which harmonic is being played. So you can say that any frequency that's not a resonant frequency will not cause resonance, because they will lose energy rapidly and they will not form a standing wave. So we can say that for this question, we say when when the a range of frequencies is sent down the so we can say that resonant frequencies are those so the wavelength that fits the co-OO. So this would be the wavelengths that fit the co-OO. This means that the wavelengths that fit the co-OO, that's when the is a multiple of half the wavelength. You can say that at the open end, so there's no phase change. Undergo no phase change, meaning that constructive interference will occur with incoming waves, forming an antinode. So we can say that's maximum disturbance. So we can say the two traveling waves, which is the standing wave, will interfere I mean, they travel in opposite directions, will travel in opposite directions. And interfere constructively, which is Ci, and Di destructively, numerous times in between the open ends and depending on the harmonic played. So you say all frequencies that are not resonant all frequencies that are not resonant are not resonant. Will lose energy rapidly. Will lose energy rapidly and not form a standing wave. Alright, that's it for this question. Okay, so we can say that for question C, that should be a merit question. 4 question D, that should be an excellence level question. Not question E, question D should be an excellence question. Okay, so if we look at question 2, sound waves interference patterns. James and Tara take two portable speakers out of the school field and place them 1.25 meters apart. They send a signal via the computer to play a frequency of 2.5 times 10 to the power 3 Hz out of both speakers at the same time. They walk along a line of A to B parallel to the speakers that are 20 meters away, as shown below. They notice a regular series of loud and quiet dots around the line and decide to investigate the pattern. James stands along the central line, and Tara stands on the first adjacent loud spot on the line, so we can say that's the n equals to 1, that n equals to 1 order. So that's the antinode. So calculate the angle of theta that Tara makes with the central line, so we can say n lambda equals to d sine theta. And where this is the first order, so n equals to 1, so 1 times lambda equals to d sine theta. V equals to f lambda, so we know that 340 equals to the frequency, which is 2,500 times lambda. We should find that lambda equals to 0.136 meters. So we say that 0.136 equals to d, which is 1.25 sine theta. So if we get our calculator here, alright, so we should find that theta equals to 6.25 degrees, okay, for SF. And this should just be another achieved question here. Distance between A and B is 10 meters. Calculate the total number of loud spots that students could hear along this line, while both speakers are producing the same frequency of 2,500 Hz. Alright, so for this question, if we want to calculate the amount of loud spots, we need to find the maximum order that occurs at the end of the line. From A to B is 10 meters, meaning from the distance from A to the central maxima or B to the central maxima is 5 meters. So this distance here is 5 meters. And if we draw a line from so we're trying to find this angle theta, and we're trying to calculate and our purpose is to calculate how many of these loud orders can fit in this angle spectrum. So we're going to be using n lambda equals to d sine theta again. And then we're going to be able to figure out how many loud spots occur on one side of the central maxima. Then we're going to add the same on the other side of the central maxima. And we're going to add the central maxima itself, which is also a loud spot. Okay, so that means we should have 2n plus 1 as our final. So loud equals to 2n plus 1. So there should be an odd number of loud spots. So we can find the angle by using our Pythagoras tan rules. So tan theta equals to 5 over 20. Alright, so you should see that theta equals to 14.04 degrees. Okay, so now we say that n lambda equals to d sine theta. So n equals to d lambda sine theta. So for n equals to distance is 1.25, sine of 14.04 all over the wavelength, which is 0.136. 14. Alright, we should find that n equals to 2.23, meaning that since it's 2.23, it's not actually 2.23 loud spots. That's not very possible. What this means is that there's actually 2 full loud spots that can be heard from the central maxima to A. So n equals to 2 loud spots. So therefore, total equals to 2 on both sides. So 2 on both sides plus the central maxima. So that's 2 plus 2 plus 1. Which equals to 5 loud spots there. Alright, and that's our final answer for this question. Okay, this question should be a merit level question, but it does have the potential to also be an excellence level question. Okay, this could be an excellence level question. I'm just going to write, could be excellence, could be merit. Okay, could be either or. Not too sure there. Definitely has potential to be an excellence for that question. Okay, so question C. James and Tara find 6 identical speakers and line them up 0.5 meters apart. See the diagram below. They play a 2500 Hz frequency sound through all the speakers. They then walk along the line A to B parallel to the speakers as before. Describe and explain the difference in the loud and quiet sound patterns as they hear as they walk along the line compared to when there were only 2 sources of sound. Alright, so the things we need to mention here is that since there are more speakers, there's now more point sources, meaning there are now more areas of constructive interference and destructive interference. This means that for a particular loud spot, a particular antinodal line or a loud spot can only occur when all of the waves arrive in phase, meaning that there's combined constructive interference. Since there are more areas of constructive interference because there are more speakers, the loud spots that they do hear is going to be louder than before than when there was only 2 speakers. So the loud spots are going to be more intense. That's our first difference. Our second difference is that since all of the waves must be in phase to produce the loud spot, this is going to happen less frequently since there are more there's more waves, meaning that there's more opportunities for waves to arrive out of phase, meaning that the times they do arrive in phase are now more narrow. So this means that the distance, the total distance, in terms of the narrowness of the loud spots is now going to be more narrow, meaning that the amount of distance that they're going to hear a very loud sound is going to be decreased. We also know that due to this setup, the distance between the sources are now decreased to 0.5 meters. We know that n lambda equals to d sine theta. D is inversely proportional to sine theta. That means if d decreases, that means sine theta will increase. That means the distance from each adjacent loud sound will also increase. So those are the main 3 differences we need to state. Okay, I'm just going to bullet point this one out. Okay, so the first difference we need to note down. First difference is that more sources mean more areas of Ci and Di. The areas of Ci for a loud sound will have more waves in phase, will have more waves arriving, causing a louder sound, louder and more intense maxima. That's our first difference. Our second difference is that waves arrive fully in phase. So waves arrive fully in phase. So that's from all sources. As there are more opportunities for some waves to arrive out of phase. There's more opportunities for waves to arrive out of phase, hence the areas of CI are more narrow. So this is a more narrow maxima. So we can say that distance between the sources decrease. So since I'm just going to bullet point this one, so n lambda equals d sine theta. So we can say that d is inversely proportional to sine theta. This means that interference occurs at larger angles. So interference at large angles, larger distance between loud and soft sounds. Alright, that's all we need for that question. Question D. Explain the effect on the spacing of loud and quiet spots if James and Tara played a high frequency. So n lambda equals to d sine theta. We know that as v equals to f lambda, v stays the same medium. Remember that speed only depends on the medium. F equals to 1 over lambda, meaning the wavelength decreases. Alright, so we say that basically, since there's very small space here, I can't really fit everything, so I'm just gonna talk to you guys about those questions. Okay, so v equals to f lambda. You need to state that the velocity of the sound waves only depend on the properties of the medium, the physical properties. We're not changing that. Velocity stays the same. Therefore, f is inversely proportional to lambda, meaning that if f is increased, then lambda will decrease. The wavelength will decrease. Okay, so now we can say that lambda is proportional to sine theta. That means interference occurs at smaller angles. Okay, so interference occurs at smaller angles. If interference occurs at smaller angles, okay, so just link this one to he can link this one to less. Like he could directly just link it to less distance between loud sounds. Less distance. Alright, so you just need to link those few bullet points, not too many bullet points. There you just say wavelength is decreasing and interference is occurring at smaller angles. And we can say that this means that there's less distance between the loud and quiet sounds. That should just be a merit question. You just need to link those three together. So here to wavelength decreasing, to interference at smaller angles, to less distance between loud and quiet sounds. That's just 3 points linked together. Question B, if you can state all three, you should get either a merit excellence grade, either or, I'm not too sure. And getting 1 or 2 could get you an achieved grade. Alright, so question 3, a Doppler experiment. The speed of sound is 340 meters per second. Lily and Dave are conducting an experiment to measure the frequency of the sound produced by a car horn as it travels past a station observer. Lily drives her car from point A to point B, directly past Dave, who is recording the frequency of the sound waves as shown below. Using the data recorded, Dave was able to plot the frequency observed on a graph. Using the graph, state the frequency as Dave hears as the car travels towards him. So when the car is traveling towards him, he's going to hear a higher frequency due to the Doppler effect. So we're going to say that this is occurring at this stage here. So that's 900 hertz. Okay. So he hears 900 hertz at that point. By considering the motion of the sound waves from the car horn, give reasons why Dave's meter detects a change in frequency as the car approaches him and goes past him. For this question, we're just going to talk about the Doppler effect. So we can say when the car is traveling towards him, there's a relative velocity towards Dave. This relative velocity means that since the car is traveling towards Dave at the same time as producing waves, the same number of waves is going to be concentrated in a smaller distance. That means the observed wavelength that Dave is observing is going to decrease. The speed of the wave is going to stay the same once again because we're not changing the physical properties of the medium it is traveling through, and therefore we know that the observed frequency will increase. When the car passes him, the car is directly passing him, there's no relative frequency either away or towards Dave, meaning he's going to hear the exact same frequency as the driver. After the car goes past him, he's going to hear a lower frequency as the relative motion of the car is now away from him, meaning that it's actually the motion of the car results in a larger distance between adjacent wavelengths, causing a higher observed wavelength and therefore a lower observed frequency. I should say, when the car is traveling towards Dave, velocity of wave towards Dave, towards Dave. Causes adjacent waves to be closer to the previous wave rather than if the car was stationary. Alright, so we can say that so we can just link this one to observed wavelength is decreasing. So we can say V is the same, meaning that V equals to F lambda. F is inversely proportional to lambda, meaning that observed frequency increases. And so we say when the car is passing Dave, he hears the actual frequency. At that point, and then you can link it to afterwards the frequency decreases as the car drives away. Right, I would write more, but then since there's not enough space, so when the car's driving away, you can just link that to, since the car's driving away, each time that the car produces a successive wave, it's already traveled some distance away from Dave, so technically the distance between the previous wave is going to be increased, causing an increase in the observed wavelength and then a decrease in the observed frequency. So question C, using the information from the previous wave, using the information from the previous page, calculate the constant speed of the car that Lily is driving. So when the car was approached, okay, so first we write down the formula, of course. So observed frequency equals to the actual frequency times the speed of the wave over speed of wave plus or minus Vs. When the car is coming towards Dave, okay, he hits 900, so we write that down. So 900 equals to actual frequency, we don't know, times of 340 over 340 minus Vs. When the car is driving away from Dave, we know that he hears 800. He has a frequency of 800 hertz, and this equals to the actual frequency, we don't know, times by 340 divided by 340 plus Vs as the car is driving away. So now, in order to cancel out, because now we have two unknown variables, so individually we cannot solve these equations, we're just going to end up in a big loop. Easiest way to do this question is that we just divide out both of these equations and we just leave one variable. Since frequency here, the actual frequency here remains the same in both cases, we can easily cancel this out by dividing the two equations. So we can say that 900 divided by 800 equals to 340F over 340 minus Vs divided by 340F over 340 plus Vs. So for 900 over 800, that equals to 340 plus Vs, because when we divide by a fraction, we just multiply by the reciprocal. So 340 plus Vs over 340 minus Vs. As you can see, the 340f, 340f, they cancel each other out. So now we just have constants with reference to one specific variable, which is the speed of the source, which is what we're after. This is very helpful. Sorry. So this is very helpful because now we can find out the velocity of the source. So 800, so we can cross multiply. So 800 times 340 plus Vs equals 900 times 340. So now we're just going to expand the brackets. Okay, so 800 plus 800 Vs, that equals to 900 times 340, which equals to 306,000 minus 900 Vs. If we pull everything to one side, we should see that 1,700 Vs equals to 34,000, and therefore Vs equals to 20 meters per second. Alright, that's our final answer for this question, and this should be a excellence level question, in my opinion. This should be a very solid excellence level question. To get a merit, if you can, for achieved, if you can just write down these two equations, that should be enough. That should be evidence for an achieved. If you want to get a merit, I think you need to show some evidence of manipulating the equations. So probably up to this step could get you a merit, or maybe even up to this step, either or, could get you a merit. Yeah, so question D. After Lily passes point B, she decides to accelerate away from Dave, who remains in the same position. Use your knowledge of the Doppler effect to explain how and why the frequency that Dave hears changes during this time. So when the car is traveling away, firstly, as I was just explaining in the previous question, because of the relative motion of the car away from Dave, each successive wave is going to be produced at a larger distance to a previous wave. Observed wavelength would increase and the observed frequency will decrease. However, when the Lily is speeding up, the relative velocity away from Dave will increase. That means that each second or each unit time, the car is actually moving a larger distance than it was before, meaning that it's actually going to be a larger distance between the previous wave and the new wave that's being produced, meaning there's a larger difference between the two distances of these waves. That means that the observed wavelength is going to further increase, which means that the observed frequency is going to further decrease as the car speeds up. So we can say that when the car accelerates away from Dave, the relative velocity away from Dave increases. This means that so a larger distance will be observed, so hence there is an increasing observed frequency. So you can say since V equals to F lambda, V is constant. So we say it depends on the medium, which stays the same. So since V is constant, now we can say lambda proportional to 1 over F, meaning observed frequency will gradually decrease. Right, and that's that question, and that should just be a merit level question. You just need to link it to the observed frequency gradually decreasing. That should be a merit. And in terms of that question, for question A, should be achieved. Okay, that's very simple, straightforward question there. question B, that should be a merit level question. In case you just link the different things that's happening when the card's approaching Dave, when it's just passing Dave, and when it passes Dave. Alright, and that's it for this paper. I hope you enjoyed this video, and I hope to see you all in the next one. Thank you. Bye.